All right, welcome back. We're going to talk more about wave-particle duality and the de Broglie relation and get a little bit more quantitative about this. So remember that the de Broglie relation tells us, and wave-particle duality tells us that all particles, all things are things, but they also have a wave-like character. They're wavy, they're curvy, they have something that makes them a wave. So for a regular wave, also remember that the characteristic of the wave is a wavelength, and we call that lambda, and it's the distance between the similar zero crossings of a basic wave, right? So you've got nodes, you've got an upward going wave, goes back down across zero and comes back up, and that distance between the repeat distance from the upward going node to the next upward going node is the wavelength of that wave. Now remember, what de Broglie taught us was that the wavelength, lambda, has something to do with how fast that object is going, the particle. Or really what it has to do with is the momentum, the absolute value of the momentum, the magnitude of the momentum of the object. And the simple relationship, again, is that the wavelength is this constant Planck's constant divided by the magnitude of the momentum of the object. That absolute value sign means magnitude. It just says, since the vector, the momentum is a vector, it points in a certain direction. We want to know how big the quantity is. And for the wavelength itself, we don't care about the direction itself. Now let's look at this in a little more detail, because the de Broglie relationship is what we call an inverse relationship. The wavelength depends on the Planck's constant divided by over the momentum. Or you can write it the other way around. The absolute value of the momentum is equal to Planck's constant divided by the wavelength. So first, if we have something with very, very high momentum, we have this very short wavelength here, lots and lots and lots of zero crossings over a given distance. We've got a short wavelength and a long or high momentum. The other possibility is a very long wavelength wave that has very few zero crossings, very low wavelength, and very long wavelength and very low momentum. Now, one of the cool things about quantum mechanics is this exact same relationship applies to photons, applies to light as well. So with light, once again, the momentum of a photon is equal to Planck's constant divided by the wavelength of that photon. And that's kind of incredible. So photons, which don't have any mass, nonetheless carry momentum, as we discussed before. Also, for each photon, there's a certain amount of energy, and that energy is equal to Planck's constant, again, times the frequency of the photon. So E equals h nu is one of the fundamental relationships. That's also equal to h, Planck's constant, times the speed of light divided by the wavelength, and finally, it's equal to the speed of light times the absolute value of the momentum if we take the de Broglie relation there and substitute in for the absolute value of momentum for h divided by the wavelength. So once again, this means, I mean, basically this really does work. Light sails actually work. NASA has projects to deploy satellites that near the sun, where there's a great deal of light, to actually use the reflection of light to steer satellites. So this is, we're not making this up, this actually happens. But the other attribute of photons, in addition to having a wavelength, is that they really are individual things. We can count them. We count them one at a time. We do this all the time in the laboratory, in my own laboratory and many, many labs, using these devices called photomultiplier tubes. Photomultiplier tubes fundamentally rely on this thing called the photoelectric effect, which was one of the experiments that was conducted at the very dawn of quantum mechanics. And the photoelectric effect is actually the thing that won Albert Einstein his Nobel Prize. It wasn't relativity and all that stuff. It was this seemingly mundane thing called the photoelectric effect. He wrote the paper in 1905 and ultimately received a Nobel Prize in 1921. So now let's see how this works. Let's think of it in terms of the experiment, the observations in the experiment. First, what we're going to do is we're going to shine light on a metal surface, and that metal surface is going to be held in vacuum so nothing bumps into anything, and it's a clean experiment. And we're going to measure the kinetic energy of electrons that get kicked off of this metal surface. You just have to believe me that we can do that. So what's going to happen is we shine light on the metal, and we find that electrons come sailing off of that metal surface when the light is absorbed. Those electrons are called photoelectrons. So the first thing that's observed is if you make the light brighter, you turn up the intensity, but you keep the frequency of the light the same, the energy of the electrons doesn't change at all. You just get more of them. So the more light you shine on the object at the same wavelength, at the same frequency, the more photoelectrons come off. The second observation is that if you actually dial up the frequency, you make the light bluer, then the energy of the electrons actually goes up, and it goes up linearly. If you double the frequency of the light, you're going to double the energy of the photoelectrons. However, the third observation is that below some critical frequency, if you can make the light too red, you don't get any electrons at all. The light just disappears, nothing happens, you don't get any current in your picoammeter, and you see no signal whatsoever. So those are the three critical elements of the experiment. Okay, so let's see how this photoelectric effect plays out when we plot some data. So first of all, we're going to start with an x-axis. The thing that's being varied in the experiment is the frequency of the light. And in frequency space, on the left-hand x-axis, we have basically red light, which has a low frequency, and on the right-hand side, toward higher frequency, you get bluer light. And then what we're going to measure on the y-axis is the energy of the photoelectrons that come off. And actually that energy is usually, and physicists call it electron volts. So don't worry about the units, but that's what they usually are expressed in. And now we go in the laboratory, we do an experiment, and we measure some of these values. So as we go to higher and higher energy, bluer and bluer light, higher and higher frequency light, we see the energy of these photoelectrons increases, and it's pretty much a straight line. Looks something like this. And that experiment might be for one specific metal. We'll call that metal number 1. We replace the metal inside the vacuum device, set up the experiment again, and once again, as we get bluer and bluer and bluer, the energy of those photoelectrons rises, but at any given frequency of light, the energy might be a little bit lower for metal number 2, and once again it makes a nice straight line like this. So now we can measure the slope of that line here. We find the slopes of those two lines are exactly the same, which is kind of interesting. They're parallel lines, and then when we go and calculate that slope, lo and behold, it's that magical constant h, Planck's constant. So that's the basic setup of the data of the experiment. Now we get Einstein's theoretical interpretation of these results. So the first thing is that the light is presumed to be arriving in individual chunks that we're going to call photons, and the energy of those individual photons, as we've seen before, is given by Planck's constant times the frequency of light. So that's E equals h nu, that famous formula. Now the second thing is that the electrons in the metal are presumed to be bound. So there's a certain energy that's holding them in the metal, and we call that energy the work function. And it looks kind of like this. We've got energy on the y-axis. The binding is some sort of what we call well. So we'll draw this little dip here. And the energy difference between the bottom of the well, where the electrons live, and the top of the well, where they're free to float around inside the vacuum, we're going to call that capital phi for the work function. So it's pretty straightforward to derive that the energy of those electrons, photoelectrons, which we indicate with E minus typically, is equal to h nu. That's the energy of the photons that get absorbed. But then you have to subtract off the energy it takes to get out of the well, which is that work function phi, and that's characteristic of a given metal. So the more photons you shine on this system, you just kick off more electrons. Basically every photon potentially can kick off an electron. So the increase in the intensity of light, which is more photons at a given frequency, just gives you more and more electrons, gives you more current. So to summarize this first set of lectures, we've learned now that there are essentially three things that we have to pay attention to: the photon, the proton, and the electron. And we know the necessary properties of those three things. All of these things have a wavelength, and it's always given by this de Broglie relationship. The wavelength is equal to Planck's constant divided by the magnitude of the momentum. And we can also write that the other way. The magnitude of the momentum is always equal to Planck's constant divided by the wavelength of the object. One photon has an individual energy. It's a chunk, and the energy of that photon is equal to Planck's constant again times the frequency of the photon. Everything is both a wave and a particle. This concept of wave-particle duality is central. And for photons, we have this photoelectric effect where two of our hero particles get connected to each other. When we shine light on a metal, the energy of a photoelectron that comes off is given by the energy of the photon coming in, which is h nu of that photon, minus the binding energy of the electron in the metal, which we call the work function, capital Phi, which is specific to the metal.